It's really strange to me how scientists have labeled the strong nuclear force gluon field. Gluon charges, they use red, green, blue, anti-red, anti-green, anti-blue instead of actual mathematical equations. For example, when you add red, green, and blue, you get white, I guess, and that's supposed to be no charge. Um, so an anti-red would just be a blue and a green, because blue, green, and red makes white light. There's a better way of doing this. By using complex analysis. Just to refresh everyone's memory, if we have a unit circle, this is 1, this is -1, this is I, this is -I. So 1 equals e to the I2 pi, I equals e to the I pi over 2. And these are just the angles right here. For example, here would be I pi over 3, 2 pi over 3. Here's I pi over 2. Here's pi. These are just angles and radians. Gives you the spot on the unit circle. Now, if we take these three angles right here, now these angles right here, -1 and 1, this could be the electron and that could be the positron. If we do that, then these angles here will give us -1/2, 1/2, and 1. And what's special about that is if you add those three angles, you get 0. And if you add the only problem with that is the ratio is -1/2, -1/2, 1, and we want a ratio of -1/3, -1/3, and -1/3, -1/3, and +2/3. So we can do that by putting a factor of 2/3 in front of these coefficients, or sorry, these angles. And then when we take the real parts of 2/3 e to the I 2 pi over 3, you get -1/3. And then the real part of 2/3 e to the I pi 4 pi over 3, you get a -1/3. And the real part of 2 over 3 e to the I 2 pi, you get 2/3. And these are the charges of the quarks found inside of, let's say, a neutron, I guess, using that as an example right now. So we have our list of quarks and anti-quarks. So these are our three quarks, and this is just arbitrary. These could be our quarks and these could be our anti-quarks, or you can give them a rotation or whatever. So as we said, the electron is e to the I pi, so angle pi puts us here at -1. Positron is right here at +1, angle is 2 pi. And then these angles right here correspond to a smaller circle within, so it's not a unit circle, it's the unit circle divided by, multiplied by a factor of 2/3. So we would do this right here, and then these angles would be somewhere over here. 2 pi over 3 would bring us, I believe, right here. And then, I don't know why that looks like a dot. That shouldn't be a dot there. The next angle would be here. Sorry, that's not right. The first angle would be here. That's I to the 2 pi over 3. The next angle would be here, which is I to the 4 pi over 3. And the next one would be here, which is I to the 2 pi. So interestingly, what happens is when you add all of these angles, you get 0, or if you add them to any of their, I guess, negative angles, you also get 0. And when you add all these together, you get 0 as well. And then, yeah, this is a better model to use than just red, green, blue. Another reason is because these also give you imaginary factors as well, not just the real factors. And that might actually mean something in the universe. This actually, I mean, is it a coincidence that these numbers, you know, the 2/3 and the 1/3, like, is it a coincidence, or, you know, is there something deeper in physics that we can figure out from looking at the imaginary numbers here as well? And that's why I think it would be better to use angles instead of colors to describe the strong nuclear force. That's assuming that it actually does exist, and that's how quarks actually behave, is by interacting with each other with the gluon field. But yeah, so that's it.